All right, so that last video ended with this sentence at the top that if we start with any rational number, we know we can construct that. You did some examples for homework. And then if all we do is add numbers, subtract, multiply, divide, or take square roots, we know we can do all of those things through constructions. We have a construction operation to do all of those things. And so if whatever numbers we end up with doing those operations are constructible, we can figure out a pattern for how to make them. So what we want to do now is write this down in a more formal way. And the notation here is going to get a little bit funky. I'll show you the theorem in a second, but first let's see if we can draw what we're talking about. So what it is, we know that we can make all rational lengths. Okay, so we know that given any integer over integer, I can make anything of that length. I'm going to call that field K0, or it's Q. Then, once I've made all the rationals, I know I can start taking square roots. So I know that my field of all constructible numbers is going to include the square root of d0 for some d0 that's a rational number. Okay, so for example, in the example I did in the last video, my square root of d0 might be root 5. I knew how to make length 5, so make root 5 also. All right, then we can do another step in our construction. Another step in our construction might involve, oh, and let me give you a little more notation. I'm going to call that set K1. It might say, okay, I know how to make everything in K1 now. Let's add on another square root. So let's take something from K1, take its square root, and construct that. So D1 is going to be something in K1. So for example, in that one that I talked through in the last video, the square root of D1 might be where I say, all right, I know now how to make 3 minus root 5. Let's take the square root of that length. Okay, so I can keep doing this kind of thing. So maybe I'll write one more. My next set in this chain, the next thing I do with my constructions might be taking this whole set, which I'm going to call K2. I know I can construct it. Now let's add on a square root of something D2, where D2 is in K2. So this might be the step where I know now I can make 1 plus root 3 minus root 5, and so then I say, let's take that length and let's take the square root of it through our construction, and that might be what I mean by the square root of D2, and we can keep going like that. All right, so the way we write this down, this idea of at each stage of a construction, the only sort of new operation I can do that extends my field is with square roots. The way we write this down is this theorem. So this notation gets a little heavy, but this is our sequence of fields like we saw up above. So K, or Kn, here's Kn is the same as K, is our field of all constructible elements. K0 is Q, it starts at Q, and at each stage, K1, for example, is K0 root D0, just like we drew up above. K2 is K1 root D1, where that D1 is in the field K1. All right, so we just talked through one half of this proof. So this theorem is an if and only if. And we just talked one direction, which was if alpha lies in a field with subfields like this, then alpha is constructible. And we didn't write down a formal proof, but we talked through all the steps. So if we knew alpha was in a field with these subfields where each extension was just a square root extension, then we knew based on those homework constructions that we could construct that element alpha. The other direction is going to be harder. So our other direction for this is if alpha is constructible, then we want to be able to say it lie in one of these set of field extensions. But we don't know that right now. So for example, so let me rewrite this. If A is constructible, is cubed root of A constructible? So we know we can construct the square root of A using some similar triangles, but can we do the cubed root of A? Or can we do the fifth root of A? Or lots of other things like that. And maybe there are other operations that we're not sure if we can construct or not. I gave you a set of I don't know, 5 problems maybe, and you did a bunch of constructions to see what you could do, but maybe there are more I could have given you. So we want to think through that. Another thing to think about here is, can we construct a segment of length pi? Or maybe E. So how do we know what length segments we can construct and what we can't? That's our question. And the way we're going to study this is by thinking about exactly what a construction is. And what a construction is a set of steps, each of which is just drawing lines and circles. So constructions are drawing lines and line segments between 2 points that we knew we could construct, drawing circles with a center point and a radius that we could construct, intersecting 2 lines, intersecting 2 circles, or intersecting a line with a circle. That's it. Those are the only things you can do with a compass or straight edge. You can draw lines, you can draw circles, and you can look for intersection points of those things. So what we want to study is the algebra of these operations. So we're going to take this and turn it into some algebra on the xy plane. And the algebra I mean there is like the high algebra. We're going to be looking at some equations of lines, equations of circles, and thinking about what the intersections look like. That's going to help us figure out, when we do all of these steps in a construction, what exactly are we doing in terms of the numbers and the lengths of these segments that we have.